How's it going, everyone? So in this video, I wanted to go over how we actually assume the signs that we do or the directions that we do for the internal force systems when we actually take a load-bearing structure like a beam or a column and we pass a section and we segment it. So the first force that I wanted to talk about is the actual normal force. And if you remember, the normal internal force is perpendicular to the surface of segmentation. And what the book is trying to show you up here in the upper left, this is actually not a figure taken from your textbook, it's a figure taken from something else, is that when an actual beam or a horizontal member is subjected to external forces that would tend to put it in tension, that we'll call that a positive normal force. So this is a scenario in which we would have a positive normal force. So this explains why we actually assume the direction of the internal force system, particularly the normal component, that we do when we pass a segment. So if we were to pass a segment and we're to segment this into two halves, notice that, and I'll kind of draw the jagged lines to show the idea of a segment. On the left, we have the external force, which is pulling this to the left. And in order for it to stay in equilibrium, it must be that the internal normal force points to the right. And by Newton's third law, if the force acting at the point of segmentation on the left points to the right, then on the right, it will point to the left. So this is why you have the sign convention that you do if this external force system is applied. So the ideal is that by convention, we call a positive normal force an external force system that will tend to actually put this beam into tension. And in that case, in order for the body to maintain equilibrium, if we were to pass a vertical section, the internal normal force on the right would point to the right, or I should say the internal normal force on the left would point to the right, and the internal normal force on the right would point to the left. So that's why these two are external. That's why when I showed you the initial diagram that I did for the internal force systems, that when we were looking at the portion of the beam that was to the left, the internal normal force pointed to the right. It's because we're assuming that a positive normal force would associate with actually putting that beam into tension by pulling it on both sides. So we talked about the axial or normal force in this case. Now let's talk about the positive shearing force. So if you notice, we're calling a positive shearing force a force that would tend to kind of shear the left portion of the beam up in the right portion of the beam down. So if I go over to my dot cam again, and I won't show you this every time, I promise. I know it's kind of boring, but here's the left portion of the beam going up. Here's the right portion of the beam going down. If I have a force system that tends to induce this type of shearing stress, what I notice is if I segment my body, since the external force is actually pushing this left portion up, the internal force, the internal shear, must be going down. And same idea vice versa. If on the right side this is going down, then the internal must be going up. Notice that these also are Newton's third law of reaction pairs, which explains why they're equal and opposite. So that's, again, why, just showing if we have a segmentation of a beam and we're trying to calculate the internal forces, we assume that the normal force went to the right and the shearing force actually went down. So there. And note that some books call the normal force the axial force, as you see in this case. Last thing is what does the actual sign convention for the internal bending moment look like? Well, if a beam is actually tended, if the external forces are tending to bend it in such a manner that it takes on a concave down shape, we call that a positive bending moment. So you can kind of see if you were to do a segmentation here, I won't go to my dot cam and make an ugly drawing, that in order to counterbalance that and for both portions to be in equilibrium, the internal bending moment acting upon the left portion of the beam must be counterclockwise, and the internal bending moment acting on the right portion of the beam must be clockwise. So that's how that all comes about. Another thing you should know is oftentimes when you actually have a negative bending moment acting on a beam and it's tending to bow it up in that concave upward configuration, that is often referred to as hogging. For those of you that are going into more of a structural engineering point of view, that's a term that you probably want to know, and this is referred to as sagging. So positive bending moments will tend to induce sagging in a beam. Negative bending moments will tend to induce hogging. So we're going to continue to apply that convention as we move on to the remaining problems within Chapter 7.